So why is resonance important? Okay. It's the ability to rearrange your highest energy electrons throughout the structure. Okay. By causing those general shifts, you can change potential reactivities. Okay. So one of the things that we addressed, or I kind of talked about, is that if we looked at our carbonate and said it now reacts with H+, if I've got my charges attached on my resonance structure, good thing I drew those in, what would my result potentially look like? I'm going to leave the lone pairs off for the moment. Actually, I'm not going to do that because I'll yell at you for leaving them off. Okay, I'd have to attach the hydrogen to one of those oxygens. You'll notice that I did not attach it to the top oxygen. Why not? Didn't have a negative charge. Okay? So by specifying that formal charge, I know something about its reactivity. Looking at resonance can help me see where the negative charges are held. So that if I look at all of the resonance structures, let's see, did I draw them all? Damn it. If I looked at all of my individual resonance structures, I would notice that I have what charge on every single oxygen. Those dots are there. If you look really, really closely, I am drawing the electrons. Which oxygen holds the negative charge? What do you mean the single bond one? Top, left, or right oxygen? All of them hold the negative charge, which means all of them are equally reactive. All of them have the potential for picking up that hydrogen. Okay? It gives me an idea of the reactivity of the molecule by looking at all of those resonance structures. Okay? That idea is very important. Okay? So now the question is, how do I get between each of these resonance structures? Okay? Let's say that I went through Mike's long, hard way of drawing our Lewis structures, and we're like, oh man, that was way too much effort. I wish there was a shorter way, instead of having to go through and draw all those rules for Lewis structures, to be able to get between these. You better reconnect. Okay. So, any way we look at it, what we're trying to do is show how the electrons move around our structure. Right? Again, drawing too many pairs of electrons. So how could I move from the leftmost to the middle one? What changed?
Location, the double bond.
Double bond location changed. Okay, so how could I draw some stuff on top of that first structure so that I can show how I get here? So this is an interesting statement. What you suggested was that we show an arrow from the non-bonding electrons moving in this fashion. Right? Why'd you show that?
Tell you what you would get if you were to draw it.
But we said the double bond was what moved, right? Why not just do that?
That's not what happens.
You gotta get rid of it.
Why is that not what happens?
Breaks out.
Lovely statement. Draw the result. So this is something that you will hear me incessantly get you guys to try and do. Draw your result. What happens if you do that? What we are saying is that by using that arrow, we are taking 2 electrons. We know there's 2 electrons because the arrow is double-headed. And I'm putting those 2 electrons in the space between that oxygen and the carbon. What else have I done? Nothing. So nothing else can change to my structure. So the end result would be something along these lines. Where's my double bond? Exactly where I wanted it to be. What's wrong with that structure? All the bonds are there.
You got 10.
The electrons aren't in the proper space. Remember how I said you should always draw your lone pairs? Why should you always draw the lone pairs? Now you can't tell. Okay? You need the lone pairs drawn in there because if you show me this arrow, you're going to lose all credit. Okay? Because that arrow results in an invalid structure because of where the lone pairs are located. This is why you need to show the lone pairs so that you don't make that mistake. Further, that in that process, your last step, and I'm glad I just deleted all that, is you would calculate formal charge and check octets and realize the structure you just drew was horribly wrong. Okay? This is why Lewis structures are important. You need to be aware of balancing those electrons out. It is not, this is the answer. I know that when I draw this out, my result, sorry as I just kind of gag on my own tongue. Oh, I know it has to be this, so now I'm just going to draw in my lone pairs. And since he told me that, I had to draw arrows, what a jerk showing me that. Well, this is what happened. No, that's not what happened. You said, this is the answer I want. I'm now going to show whatever I have to get it to that answer. Very dicey maneuver. Okay? Let the electrons move and show you the answer. That's what we're working on. You do not know the answer, period. The work shows you the answer. If your work is solid, you get the answer. When you get frustrated, like, why am I getting this wrong? It's because you told me what the answer was and then tried to show the work. Knock it off. Show the work, the answer follows. Okay? 151, they rail about what? Units. Why? Your units show you the answer. If you go through and jump to the answer and try and fudge your units back through it, sometimes you get lucky and get it right, sometimes you don't. Organic is nowhere near as forgiving. If you think you know the answer and then try and fudge your work, you're wrong. You're graded straight up on your work, you're now dead in the water. You do not have that luxury. Show your work. Okay? So,
if we were to do the bonds jump and then show two electrons moving from one atom to the other, that would still be wrong?
So there's an interesting idea. You're saying that now we should take these and throw them over there. Right?
Would that still be wrong?
Okay. What did we just do with that pair of electrons? So I'll agree that gets you to this structure. These then pair of electrons did what? Into the vacuum? Is that a really easy thing to do? Like ionization energy, which is an endothermic process, requires massive amounts of energy to remove one electron. You're now trying to remove two, and then somehow have them go out into the vacuum, not react with anything else, and come back in. No, that's a bad idea. Okay? So this comes up with ideas on how we can move electrons. Electrons can only move through atoms and through bonds. Okay? So if we were to try and do something like that, well, we could say, okay, if I can only move through atoms and through bonds, then why don't I just do this? Good question. You should do that. That gets you to the correct answer. Okay? So move your electrons through atoms and through bonds. Yes?
So a practical example of that would be like a copper wire. If you're running a current through a copper wire, those electrons move through the copper atoms.
Mm-hmm.
They go through and you basically daisy-chaining them all the way down. So I guess there's destination.
Sure, and the electrons never jump outside it, right?
Yeah. No.
Unless you put another.
Yeah. So it's mostly that idea. Our electrons must pass through those atoms. So it's the same general idea. Okay? So in moving our electrons, again, I'm calling these multi-bonds because we aren't there yet on what to call it. Your electrons can move from a bond to an atom. they can also move from an atom to a bond. Okay? That's it. Those of you that have gone through chemistry a few times or seen organic chemistry before, you might be saying, there's a third answer. What's that third answer? Bond to bond, which is really electrons going from a bond to an atom and then moving from the atom to the bond. Okay? Either is valid. Where you have to be careful is that if you start jumping bond to bond, you run into a tendency of doing too many jumps. If you do it singly, you see more what's happening. You end up drawing some nasty Lewis structures in between, but you get a better feel for how it's moving around. Okay? So, I'm not going to come up with another example on my own. In your rules of resonance, find a source of electrons. It's all about how the electrons move. I remember when we talked about protons, neutrons, and electrons, and then we said, what's the first thing that it encounters? Electrons. Why? It's all we deal with, electrons. Find your source of electrons. Where do you have sources of electrons? In bonds. Okay? I need a little bit more than around atoms. Lone pairs. Okay. Are all bonds allowed to move electrons from? So no, we're not allowed to move electrons from certain bonds. Okay? Because one of the things that we have to do is that when we're looking at our resonance, we are only moving the electrons. The atoms never move. So if I wanted to say take the electrons, let's highlight them out there, and move those in here to make a triple bond. Okay? I'm moving electrons. That is perfectly valid. What is the result of that motion of electrons?
Hydrogen breaks off.
Is the hydrogen attached anymore? No. Have I changed the arrangement of the atoms? By definition, no longer resonance. I'm drawing a different structure. Okay? Which means I cannot break or move single bonds, okay, which will change to sigma bonds in probably next week. Okay? Single bonds cannot move as electrons. This means anything that is a pi bond or multi-bond is a valid source of electrons because it doesn't break the connections between the atoms. And lone pairs are a valid source of electrons because they don't break the connections between atoms. Okay? In that bond motion, okay, once I've found electrons to move around, I will move those electrons within the immediate vicinity. Bond to atom, if I'm starting with a bond, or atom to bond. Okay? Once I'm comfortable, then I'll start jumping bond to bond. And we'll look at why we want to be comfortable first with our bond to bond. It's ultimately coming down to just counting electrons. Once you've done your motion, draw the result. Remember, your work shows you the answer. You just now have to draw it. So now draw your answer. Check. Verify that the octet is satisfied. If your octets are all good, fine, you're done. Okay? If you have too few electrons, you'll need to repeat step 2. Okay? You need to continue to move electrons. If you have too many electrons, okay, now you're going to have to break something. The only thing you're allowed to break would be a multi-bond. Okay? We can only break those pi electrons. Where will we move those electrons? We could move as a lone pair. Ultimately, what we're doing is moving them away from the atom that had its octet exceeded. Okay? So let's take a look at an example here. I'm going to pick a source of electrons. Where's a good source of electrons? Double bonds. Okay? We have no lone pairs, okay? Because thankfully at this stage we're showing them. We'll mess with that later. So I'm going to pick this double bond. And I'm going to move those electrons. Okay? I said we're not allowed to jump bond to bond right away. We'll do bond to atom moves. So I'm going to go bond to atom. I'm going to move in a clockwise fashion. It does not matter which direction I go. Got all my hydrogens. What result do I end up with?
Can you have an extra electron around the hydrogen?
Where did I show that arrow? That arrow went from the bond, my source of electrons, and it went to the carbon, not the hydrogen. So that carbon has an extra electron. How would I show that in my drawing? Why a lone pair? You only said one extra electron. The bond moved 2 electrons. One of those electrons came from our original carbon, the other one came from the other carbon. So that's why we have a lone pair now in that carbon. What's the result? The top carbon is missing an octet. Okay, so that's problematic. We'll address that in a little bit. What else?
The formal charge of the other carbon that you just added the pair to is changed.
The other carbon is now formally negative. Okay. How do we know that we had that negative floating in there? There's a positive. The overall structure must remain neutral because it started neutral. Okay. Deciding now good or bad resonance structures. Okay. If we go through and look at rule 3, we're missing an octet on that first carbon. Okay, so we will have to go through and repeat number 2, play around with that in a little bit. Okay. As its own resonance structure, this is a valid resonance structure. Why show through and go in this one and say we have to repeat it? Is this a good resonance structure? No. One of the rules we kind of talked about but haven't listed yet, we've got charge built in our structure. We don't want charge. We have a way to minimize it. Okay. So now we've got a couple dilemmas to work with. We've got a negative charge, which is reactive because it's negative, but it satisfies the octet, so we're okay there. And we've got a positive charge, okay, which is reactive because it's a positive charge, and it's also, or it's missing the octet. Which one do you want to look at, the negative or the positive? Okay, I just heard a bunch of mumbling. I need something stronger than that. What?
Negative.
Negative. Okay, I agree. I want to look at the negative. Okay. Why might I want to look at the negative? We're looking for electrons. We're trying to move electrons. A negative, by definition, is a source of electrons. Okay. Positive is a lack of electrons. We can still address that. Okay. But really, we should be looking at that negative. It's a little bit easier to treat. Okay. So now I want to try and move to another structure. Okay. Nothing I've drawn here is per se horrible other than that not having its octet. So it's a bad resonance structure, but I've got one. So now what I want to do is move that negative somewhere else. See what I can do with it. How many different locations do I have to move that negative? 3 is a good answer. Why 3?
2 carbon-carbon bonds and 1 carbon-hydrogen bond.
We have a carbon-carbon bond down. We also have the carbon-carbon bond up and to the left. Why did you say 2?
Because it doesn't make sense to put it on the hydrogen.
We'll come back to that. Okay, one of the reasons why I thought you would have not said this one is because we just took it from there. That just takes us backwards. We want to move somewhere new and different. So go to the hydrogen or to the carbon. How can we move electrons? These electrons are located where? On the carbon atom. So which means I can only move those electrons to a bond. So it is perfectly valid to attempt to do this. So I'm going to move those electrons to the bond between the carbon and the hydrogen. What's the result? Wonky, I kind of accept that. I still have the positive charge. I didn't address anything with that, so that's kind of obnoxious.
Well, hydrogen can't accept any more electrons. Well, actually, I take it back. It can, because it can have 2 in its orbital, right?
How many electrons are around that hydrogen? How many electrons are in a line? 2. Where's my drawing? How many lines are there shown to that hydrogen? 2, which means how many electrons are on that hydrogen? 4. Can hydrogen exceed its octet? No. This puts us in a if too many electrons. Okay? So what we just drew was a perfectly valid drawing of what we attempted here. But we're now locked down in a structure that is horribly bad. I cannot exceed the octet on hydrogen. So now looking at this structure, I need to go back through and I need to fix my initial drawing here by considering this. I'm in this situation of too many electrons, so I will break a multi or pi bond. Where's my multi or pi bond on that hydrogen? Between the carbon and hydrogen. So I need to move those electrons. Where should I move those electrons? This is by moving the electrons away from the thing that's the problem. The hydrogen's the negative charge. That's our problem. We need to get those electrons away from the hydrogen. Where can I move those electrons? They are starting in a bond, which means I can only move them to an atom. So this structure was bad. I have to cross that out because I've exceeded octet. That's horribly invalid. But if I now do that fix, what do I end up with? Right back with where I started. What does that mean about my initial purple curved arrow? It was a bad option. It did not generate valid resonance. Okay. Those of you going through and say, well, I don't care about bad resonance. Yes, you do, because you will draw it all the time. You need to be able to recognize why it's bad. Okay? It is bad because we've exceeded the octet. That maneuver is not allowed. Okay? For those of you then going, well, I just spent now 5-10 minutes talking about this and I had to draw all that out. I'm frustrated, irritating, what a jerk. Yep, I will accept all of that. Perfectly valid. You need to have that frustration level. You have to see how you're getting things wrong before you can get them right. Okay? So, we tried to move to the hydrogen, failed. So what should we try? Carbon to carbon. What's the result? I've exceeded my octet again. This again means this structure is bad. Okay. Because I've exceeded my octet, I need to address that. We're in some weird negative state, but there's our flag. Here's a little flag. Okay. I need to fix that. How do I fix that? By breaking a multi-bond. Okay. Well, what do I have as multi-bonds? I now have two options. I have the option I just made, which I could undo. But I have another option. I already know what's going to happen if I undo that because I already did it wrong the first time with the hydrogen. So let's try the other option. What happens if I tried to move that? And by same thing, I believe what you're trying to tell me is that it would exceed an octet, and I'm going to challenge you on that. Where am I moving those electrons? To the carbon atom. I'm not exceeding an octet. Okay. I still haven't fixed this issue of a positive-negative state. Okay. But I have at least come to a structure that was equally as good as the red one. Okay. I went through a nasty blue thing, so now what I want to do is say, okay, I need to skip the nasty blue thing because I'm not allowed to draw that. How can I go from the red to the purple? Say that again louder.
More than one arrow.
More than one arrow. By adding those two arrows, I'm now moving electrons from the atom to a bond, and then I'm moving electrons from a bond to another atom. This takes me straight through to the purple option. Okay, and because I'm now out of space, I'm going to have to dogleg backwards. I'm not sure if dogleg backwards is the correct terminology, but it's close enough. Last possible option, I can move my electrons now from the atom to that next bond, which we know already is going to cause a problem where?
That carbon's gonna have.
At that carbon. So what should we do? Move the bond, and we could move that bond to the next atom. That's going to put us in a similar situation, which will still have these positive negatives, which would get us then to the next point. Instead of going from the bond to the atom, I could try and push that. Actually, no, we're going to draw that. Change my mind. All of these fun drawings, positive, negative, yeah. And we'll address shape and all that later. When we'd end up with this issue, what could we do now? Okay, we're still with this missing octet, we're still with a negative charge. Our last possible option, green is a horrible color, let's go black. I will move them from the atom to the bond. I'm going to have to erase all that stuff because I need that space. And I will end up with a structure that looks like this. Yes, no? All that fun roundabout. And you're like, man, this is resonance? Yes, this is resonance. It sucks. Deal with it. Okay. Why is this structure, well, number one, is this structure different than what we started with?
Yes.
Double bonds are in different locations. That's the same kind of thing that we talked about with our carbon dioxide, showing the triple bond versus the single bond. Okay. So we've now reached a new Lewis structure, or a new resonance structure. All of these now accurately reflect our resonance structure. We've got 5 different things drawn up here. Okay. Of those 5, are any of them better than the others? Yes. The first and the last are the best ones. Okay, because no charge. Okay. What do the other ones give us? Negative and positive, ultimately flagging us for how this molecule can potentially react and where it will react. Okay? Because we can see those charges within there. Is it possible that I could now go between my 2 black structures without having to deal with all of those individual painful steps? Yep, I heard someone say it. Bond to bond, which will force that bond, which will force that bond. So with 3 arrows, I can interconvert between our 2 primary resonance structures. Okay. How would you know that you should be using 3 arrows and not 1 arrow or 2 arrows? Drawing it. Valid answer. And the only correct answer. Well, there's one more correct answer. The other correct answer is you already knew the answer. Okay, from experience. Okay. You don't have that experience yet. Draw each and every single one of these painful things. When it comes to online homework, we have to be a little bit careful. If we include all of these as valid resonance structures with the online homework, it's going to get pissed. Why? These, while valid resonance structures are purple, blue, and red, are valid resonance, but they're not as good as the first 2. So when you're asked to draw resonance structures in the homework, focus on drawing the best possible structure you can. Questions? 2 slides of pain in an hour. Fantastic record. Okay. Okay, I'm going to skip this for a moment. Here's our big summary on best Lewis versus useful. Your priority for best, which is what you're always being asked to do, and this applies to resonance structures as well. Satisfy your octet rule first. Once your octet rule is satisfied, then you can go through and try and minimize charge. Okay? And you can minimize charge at the expense of exceeding the octet. But you can never minimize the octet. But you're exceeding the octet, that's breaking it. You can't go lower than the octet. You can go above the octet. You can't go lower. Okay? Others, and there are exceptions in that. And so are there other rules? Absolutely. Do I know what they are? Absolutely not. Okay? Does it matter? No. Okay? You'll encounter them as you see them if necessary. Those first two are going to be your primary focus. This comes back to sulfate. When we drew out sulfate, we had one possible answer where all the oxygens had single bonds. You guys were, oh yeah, that's valid Lewis structure. Yeah, but what was the problem with it? We didn't minimize the charge. Our sulfur in the single bond structure had a +2. All of the oxygens were negative. By exceeding the octet of sulfur, I can minimize the charge on the sulfate. If we go through and take a look at this next molecule, okay, it gets a little bit more complicated with the rules that I gave you for drawing Lewis structures, because those rules are primarily focused on what's it called? General chemistry.
That's a single molecule, right?
This is a single molecule. Yeah. We've got that as a possible Lewis structure. Is this the best Lewis structure? What's wrong with this Lewis structure? The carbon is missing its octet, so what do we need to do? We need to move electrons to satisfy the octet. Where do we have electrons that are movable? On the oxygen lone pairs, we'll move those down. And we end up with a little lightness in the room with this one. This species, between these two structures, okay, if I had drawn these both up, which one would you have said was the better one before we started talking about best and worst? Okay, we're getting a mix there. It's kind of hard. I told you the rule on what to do, and then I'm telling you what if you didn't have that rule. Most people would pick the one on the left. Why?
Oxygen's more electronegative than carbon.
Oxygen is more electronegative than carbon, so there's no way in hell oxygen would carry a positive charge if carbon could be carrying it instead. Okay? I agree. This is why I don't like the rule, satisfy your octet. But that is the rule we must work with. You must satisfy the octet. If I look at the reactivity of this molecule, the carbon reacts as a positive. Even though in the best Lewis structure, which atom is positive? The oxygen. So often when trying to predict the reactivity of a molecule, what you should be looking at is not the best Lewis structure, because the best Lewis structure actually hides the reactivity. What you need to be looking at is your least worst Lewis structure that's not your best. Okay? This ends up being your least worst Lewis structure, because we have most of our atoms have their octet satisfied. Oxygen has all of its electrons nice and happy. Okay? The carbon's the only thing missing. We now have something about the reactivity of the molecule. There was a hand.
I was going to say, the left, though, would be still a valid resonance structure?
It would still be a valid resonance structure depending on the question being asked. You have to be careful drawing that as a resonance structure.
Well, I guess the way I see it is that carbon is going to stick to something else.
Yeah, but then you're looking at the reaction. That has nothing to do with drawing a structure.
Yeah.
Okay? Questions on that?
I have a question on how you drew it. Did you draw one bent just because that's the way you drew it, or?
I have not talked about shape yet, so we'll get to that potentially here in just a little bit. In fact, I think I'm probably just going to skip ahead because I don't really like talking about this one. There's two topics here. You can look at charge and oxidation state. Okay. Interestingly enough, I've talked to a lot of Gen Chem instructors, and they get really confused on the difference between them, and I don't blame them because it is very confusing, the difference between them. Formal charge is really something that applies to a molecule. So even when we're going through and assigning a charge to an atom, we're really assigning that based on how the molecule is just arranging the electrons around, and that somehow builds more electrons as a balance on an atom. So the formal charge is more kind of a molecular picture of where the electrons exist. The oxidation state, or the oxidation number, is the electron balance on the atom, period. It has relatively little to do with the molecule. It's saying these are the electrons this atom owns. Formal charge is these are the electrons that this atom has preference for. I think I said that wrong. Formal charge is these are the electrons that the, I think I said that right, that the atom has preference for. Okay. Which one is more useful depends what you're doing. If you're trying to identify oxidation and reduction, it makes sense to look at the oxidation state. If you're trying to understand something about how the reaction worked, the oxidation state makes a little bit less, or makes less use. It makes more sense to look at the formal charge. Okay? There are two different ways to go through in counting them. Your textbook addresses that. There's some equations up here to calculate it. I always screw it up, so I'm just going to leave it at that. Questions? Really? Okay, fine. I'll accept that. Bottom line, when it comes to Lewis structures, we're asking you to draw hundreds of thousands of Lewis structures. Not because we're obnoxious, but what we're telling you or trying to get you to do is to come up with common patterns for the atoms that we see most frequently. So that when you see a halogen, you know that it has one bond and 3 lone pairs. When you see an oxygen, you know its neutral state is that it has 2 bonds, 2 lone pairs. When you see carbon, it has 4 bonds. Does this mean 4 single bonds? No, it has no quantification on single, double, or triple. It just does it have that many number of bonds. Okay? That is the goal behind it. Yes?
What's the red line on boron?
The red line, why would we have a red line pointing at boron? What's weird about boron?
Boron could exceed the octet.
Without a periodic table, that makes it hard to point to it. Boron is in the second row, which means it does not exceed.
Oh, it's less than.
It's less than the octet. Boron and aluminum are both goofy atoms. They are happy with less than the octet. They're actually missing 2 electrons. Okay? So we have you go through and pick those up. And then you're like, okay, well, I get all that. Why don't you just tell me that it's that? Well, what happens if the atom's now charged? Does the bonding change? Absolutely. Well, but at least when it's charged, it's consistent. Carbon, when it's positively charged, has 3 bonds. Okay? Nitrogen, when it's positively charged, has 4 bonds. Wait, that's not consistent. You're right, it's not. That's why we don't tell you to memorize it. We tell you to do it until it's built or beaten into your head. That's why you're drawing your Lewis structures. Okay? There is not a nice, easy, consistent pattern that you can use to say, oh, if it's positive, it has this many bonds. It doesn't work like that. Okay. You can try and come up with some pattern if you would like. I'm going to tell you right now, it's a horrible idea. Don't do it. Okay. So what we want you to do is to be able to recognize that if I draw a negative oxygen, you immediately tell me that oxygen has 3 lone pairs and 1 bond. That's what we're looking for, is an instant guttural response. Okay? Where that becomes dicey is not only do you need to be able to say that with oxygen, but what happens if I say sulfur is negatively charged? Sulfur's not on the list to memorize. You're right, but sulfur's underneath oxygen. Sulfur and oxygen act the same because they have the same number of valence electrons. Okay? They act very similarly, so we can predict and draw parallels between those connections. Okay? If you haven't done so already, by drawing all your Lewis structures, these things need to get stuck in your head. The issue with rote memorization is that you will likely screw it up when it counts most. Follow the patterns on drawing your structures. Questions? Yes?
Does the shift pattern hold constant?
I'm not even going to attempt to answer that question in front of the class. We can talk about it after class if you would like. Okay. Does the shape atom change the interaction? For instance, if I constantly, when we went into the tutoring center and you asked me a question and I went, well, what do you want? Is that going to change the interaction you're going to have with me? Versus me just saying, yeah, let's figure it out. Okay, let's do this. Okay. We're going to get a different response. The shape, how we look at things, will change, will change how our molecules interact. So we have to understand shape, not just bonds. Was there a so? No. Okay. So, if we went through to try and draw, if I asked you to go through and draw this formula, would everybody draw the exact same answer? I would actually bet that you would. And then what you would end up drawing me, 1, 2, 3, 4, 5, and then all those hydrogens on it. And you can see how excited I am about this slide because I'm not going to draw all those hydrogens. So I'm just going to do this. Yeah. Okay. Is that the only answer, though? Okay. We could have put carbon out here and then put the hydrogens there. There are a variety of ways that we could go through and draw this structure, which means formulas are meaningless. Do not give me a formula. What you need to be giving me is the structure. There are a variety of ways to look at that structure. In this case, we have a structural formula. This gives us a little bit more information about how it comes together. So if we start this off, what do we have? We have a C. Sound effects are awesome, I'm sure. We have a CH3 connected to Okay, so let's change an interpretation here. I heard we had 2 CH3s. How did you know we have 2? Okay, so let's put the other CH3 here. Okay, what are those CH3s connected to? A CH. What is that CH connected to? Which is then connected to a CH3. Does this still match the formula? Yeah. Does that change how this molecule interacts with its environment? Absolutely. So we have to be careful with what we're looking at. Okay? You'll notice that I've already changed how I've been drawing it. If we looked at the Lewis structure, I have to have all those stupid bonds hanging off with all the hydrogens. Okay? Really tedious. I didn't want to do that. So I abbreviated it. Can I abbreviate this further? Yes. Okay? Organic chemistry is all about carbon molecules. We're tired of drawing C's. So what do? We get rid of the C's and we specify them as a dot. How many dots are in my representation? 2. Which then means 2 carbons. Okay? So I've implied my carbons. I no longer have to draw the C's. I still have stupid freaking H's. Man, just nonsense. God, there's so many H's. I wish there was a way I could just get rid of them. Yep, there is. It's called don't show them. Okay? And why can I not show them? Because I know carbon has 4 bonds. Each of those carbons currently only has 1 bond shown, which means the other 3 are hydrogens. I can imply hydrogens out the yin-yang. This becomes a massive problem when we start to look at the reactivity of hydrogens attached to carbons. Why? We stop showing the hydrogens, which then means you run into this problem, well, I don't see how it reacts because there's no hydrogen there. There is a hydrogen there. It's implied. Watch for those hidden hydrogens. Okay? Yes?
If you had like a chlorine on one of those, would you have to actually specify the chlorine?
So let's say chlorine is attached to that carbon. How many carbons are specified?
3.
Well,
You don't really know.
but I want it to be a chlorine. I like the kind of sarcastic statement there. Write it, yes. That's how you write it. You can imply hydrogen. You can kind of imply carbon as a point. Every other atom is specified. Okay? Every other atom, oh my God, huge periodic table. Remember, we got 10. We got 10 atoms. Okay? 10 different elements to work with in organic. So it's not that many to worry about. Okay? Vesper stands for meh, not quite. Valence, shell, electron, pair, repulsion. Okay? It's now starting to bring in something about the shape, okay, which we haven't talked about. So we can introduce ideas of shape. We show that with wedges and dashes. The wedge is coming at you, out of the paper. Okay, the dash is going away. The solid lines in the plane of the paper. Really important for chapter 3 and kind of chapter 4. Okay? Depending on what we're looking at, we may start to vary, is it just vary which version of the structures we're looking at. It's all ultimately getting at the same idea. How much information do we want specified? In the case with those hydrogens, could I go through and show the wedges and dashes for the hydrogens?
Yeah.
Yep. Does it add any value for information for the molecule? Well, if I'm just trying to identify the molecule, no. If I want to know how the hydrogens react, yeah, it might be helpful to show them. So depending on what you're looking at, you will see people remove or add information to your structures. Okay? Your big simplifications. Okay? I said 10. Look at that. See if we need. Oh, there's a lot of halogens. So 8 elements that we're primarily concerned about. Okay? The next thing is we'll simplify shapes and hybridizations, which again we haven't talked about quite yet, and then abbreviated drawings. The abbreviations will bite you, so be careful abbreviating. Assume every point is a carbon atom. Okay? Unless we've otherwise specified it. Hydrogens are allowed to be implied to carbon to satisfy the octet on carbon. Okay? We will never imply hydrogens on any other atom. Carbon is the only one you're allowed to imply hydrogens on. Charges will never, ever, ever be implied, period. They are always shown. Okay? And these are our formal charges. Why? If I want you to show CH3 positive, well, I'm implying a hydrogen, right? There's an implied hydrogen floating back there. Is there? No, I need to show the positive charge. Okay. How about this as a possible answer? Does that not count as a Lewis structure for CH3 positive? Why not? I'm implying a hydrogen.
Because there's a charge there, you can't.
I can imply hydrogens whenever I want. Except when you've already drawn hydrogens on there. When is this relevant? Your online homework. I could care less. I would probably not give you credit for that, to be honest. Okay? But it's a gray enough area that you might end up getting it if you wrote that on an exam. Okay? But on the homework sees this and it says, okay, you're telling me the carbon is positive, so I need to look for three bonds, or you can just imply all of the hydrogens. But you don't have a choice. You can't mix and match. If you're going to show hydrogens, you'd better show, whoops, that's an eraser. You'd better show them. If you don't want to show the hydrogens, then don't show the hydrogens. No gray area in between, no halvesies.
So when you're applying hydrogen, you show the lines?
You do not have to show the lines. Because if you show a line, that ends in a point, which is then a carbon. So the only way you know it's not a carbon is by showing a hydrogen. Okay? Nitrogen, oxygen, halogens often have implied electrons. Okay? And we're going to end on that one being a really important topic. Okay? I'm going to try my best this semester to everything I give you show all the lone pairs. Okay? That's because I want you to show all the lone pairs. And that's because those are electrons that are able to react. If you do not show them, you lose your ability to track resonance, you lose your ability to track reactions. So show your lone pairs. Your textbook may start to imply lone pairs. Okay? This is something that is spotty and inconsistent at best across all textbooks, across all courses. Sometimes lone pairs are implied, sometimes they aren't. They are typically implied when we aren't using them. But how do you know you're not using them? you know what you're trying to do. If you already know what you're trying to do, you already know the answer, in which case, not a big deal because you already knew the answer. The textbook always knows the answer. Okay? Sorry for running a little bit late there. We are done.